So it's a great pleasure for me to be here this week in Paris. I actually enjoy it much to be back here. First of all, thanks to the organizers for inviting me and giving me the opportunity to present some of our work here today. I would also like to take the opportunity and congratulate the organizers for bringing together such a nice group of excellent researchers, and I enjoyed already a lot of discussions. I anticipate there are going to be some more interesting discussions for the remainder of this week, and I would like to use my time right now to talk about our project on Bayesian data interpretation with large-scale cosmological models. And that is actually a project that has been done in collaboration with a lot of people right now, all of them indicated there. And together we are forming the Aquila Consortium. And the Aquila Consortium is interested in developing and applying novel data science methods to cosmological surveys such as galaxy redshift surveys, but in general, any cosmological probe that we can get in our hands. And in particular, we are interested in inferring from cosmological observations the three-dimensional spatial distribution of dark matter and its dynamical formation history in order to derive some properties about the universe as a whole and the dynamic expansion history of the universe. Well, I just want to give you a very brief motivation. As cosmologists, we have a very great theoretical model. We are basically working in a gravitational context, so we have a pretty good idea about the theoretical aspects of gravity, and we can then add different hypotheses to this theoretical framework. Like, for instance, we can add the matter content of the universe as a hypothesis. We could add dark matter, dark energy, and other fluid components. We can put the hypothesis that the universe began from an almost homogeneous matter distribution, which then evolved gravitationally over 13.8 billion years. And putting all this together, we are arriving at the standard model of cosmology, and this standard model makes very testable predictions, in particular for the three-dimensional dark matter distribution. And what you can see here is one of the standard evolutionary models on lambda CDM model. We start off from an almost homogeneous matter distribution roughly 13.8 billion years ago, and then through gravitational interaction we start forming all these very detailed filamentary structures of which we have heard a lot throughout this week already. And in particular, the specific shapes and configuration of these structures, they retain a memory of the cosmic initial conditions from which they formed, but also on the gravitational processes that shaped them. So by looking at the three-dimensional density field of the dark matter distribution as a whole, we can hope to actually try to answer a great deal of the questions that we have about the universe. So unfortunately, that's how data typically looks like. These are galaxy positions in the sky. You can see that we have incomplete observations. We have a lot of noise in there. We have inhomogeneous noise statistics across the survey because we are flux limited by our telescopes. And in particular, for the next generation of surveys, LSST and Euclid, we will be dominated by systematic effects. There's another challenge that we have to address because we are now, in contrast to CMB experiments, for instance, addressing the low redshift. With the next generation of galaxy surveys, we're probing out to redshift of 3. But we'll have to address the nonlinearities in the physics model, in the data analysis framework. And just to give you a rough number, roughly 80% of the total integrated weak lensing signal expected from LSST and Euclid will be generated by nonlinear structures. So in order to make the most of these data, we need to actually develop novel methods to account for the nonlinearities of the data of the system. In particular, due to the combination of all the systematics and stochastic effects, a unique recovery of the three-dimensional density field from observations is not possible, and that's why we are here, because we have to develop statistical data analysis methods, and we believe that inferring the density field from observations can be best answered in a Bayesian framework by providing the posterior distribution. As all of you know, the posterior distribution is just the probability distribution function of the signal given some data, and it can be expressed as a product of the prior, which incorporates our a priori knowledge on the system that we are analyzing, times the likelihood, which describes the statistical process by which we have obtained the data given a specific realization of the signal. And then we have the evidence, which for the purpose of this talk is nothing else but a normalization constant. So in order to do statistical data analysis, we need to know something about the statistical behavior of the system that we are analyzing, because we have, in one way or another, developed likelihood and posterior distributions. And we are interested in actually trying to analyze these nonlinear large-scale structures. And by eye, you see that this field does not exhibit simple Gaussian statistics. You certainly need 3-point statistics and higher order correlation functions in order to describe the filamentary features in there. And in fact, even if you would try to use an infinite hierarchy of higher order moments to describe this field, it's not guaranteed that this hierarchy would close. For instance, for a log normal distribution, that is not the case. And in fact, to date, we don't have a closed form description for the statistical behavior of this density field in terms of an analytic multivariate probability distribution function that we could use to develop likelihood and posterior distributions. So, but we could step back for a second, just wonder where does this statistical complexity come from, because we believe from theory, but also from observations as obtained from the Planck satellite, that in the initial conditions, roughly 13.8 billion years ago, the initial seed fluctuations of the structures are almost homogeneously distributed and following a Gaussian random field, or realization of that to a very high degree of accuracy. So while the final density field has statistically apparently very high complexity, the initial conditions are statistically almost trivial and completely determined by the 2-point statistics. So where does the statistical complexity come from? Well, it comes from deterministic gravitational processes that basically just transmorph this initial Gaussian field into some field that has an apparent higher statistical complexity. But since gravity is a deterministic process and both fields are related via this deterministic process, this field contains exactly the same amount of information as this field. And the question then arises, if the statistics of this field seem to be so complex, but it only has the same information content as this field, why then don't we try to perform large-scale structure inference in the initial conditions where we understand the statistics and account for the generation of all this apparent complexity via either analytic approximations to a gravitational structure formation model or full numerical structure formation simulations that account for the generation of the statistics on the fly. And that's where we actually developed or started developing in 2012 something which we call the Bayesian Forward modeling approach for the cosmic large-scale structure. And in particular, that's the picture. We start by generating a Gaussian random field according to a Gaussian prior for the initial conditions. Then we use a deterministic transition, which is done by a physical model. In this case, this is a n-body simulation that solves a gravitational system. And then from the initial conditions, we arrive at a realization for a nonlinear density field. We can then add some kind of likelihood function. In this case, we are using a Poisson distribution to account for the shot noise in the galaxy distribution. And we are also using a phenomenological galaxy biasing model, a local truncated power law model, to then generate predictions for the data, which we can actually compare to the actual observations. So this is a standard forward approach that any n-body simulation does, and I think every frequentist would agree to this, because that's just the standard Monte Carlo approach. And if you would do this, you would arrive at realizations of the data. But we are not interested in realizations of the data, we want to know the realizations of the initial conditions. And that means that we have to feed back some information from the data back to the initial conditions through the physics model to get the initial conditions. And as we heard from Uroš yesterday, you can try to do this via various methods. We are going to exploit actually full Markov chain Monte Carlo techniques, where we actually try to infer the set of three-dimensional cosmological initial conditions where the parameters are the density amplitudes of the initial conditions at different grid elements in a three-dimensional volume. And typically this amounts to 10 million or more parameters which we have to infer. And that's a very challenging problem, because we have to solve a Markov chain Monte Carlo approach in high dimensions. And yes, you're right, in every step of this Markov chain Monte Carlo approach, we have to solve for full n-body simulation. So there are several techniques. We heard from Uroš yesterday that you can use optimization and variational Bayes. We want to use Markov chain Monte Carlo approaches to solve this problem. And in particular, a couple of years ago, I would have said that the algorithm that I'm talking about, the Hamiltonian Monte Carlo sampler, is a criminally underused algorithm, but by now it became quite famous. There are many public and accessible implementations of the algorithm. In particular, the latest publication of the TensorFlow package by Google has an implementation of the Hamiltonian Monte Carlo sampler. So I don't need to talk too much about it. I just want to give you a physicist's introduction to it. Suppose you're interested in exploring this probability distribution function P of x, then you simply interpret the negative logarithm of that as a potential. And when you have a potential, what you do as a physicist is you just add a kinetic energy term. In this form, we added a term that is quadratic in the momenta P, which are Newton's parameters, and we have a mass matrix M. We don't care so much about the actual parameters here. These are Newton's parameters, and we are going to marginalize them out. But the advantage is now, since we have a Hamiltonian, this simplifies the exploration of the parameter space quite a lot, because then we can actually use all the entire machinery that has been developed to solve classical mechanics problems by just following Hamiltonian equations or equation of motions in this high-dimensional parameter space. So now suppose we are starting at a particular point in this high-dimensional parameter space consisting of our target quantity x and a Newton's momentum p, and we then integrate these equation of motion for a certain amount of pseudo-time, and we arrive at a new point x prime p prime. So the nice thing, in contrast to any other Markov chain Monte Carlo algorithms, is that this algorithm does not perform a random walk, but it rather follows persistent trajectories in this high-dimensional parameter space to explore the distribution. And in particular, the forces of this equations of motions, they are basically the derivatives of the logarithmic posterior distributions. So the particles are not randomly exploring the parameter space, but they are actually attracted towards the high density regimes in this parameter space, and that's very important in high dimensions. And this makes the algorithm very efficient. To build a valid Markov chain Monte Carlo algorithm from it, at the beginning of every trajectory, we have to randomize the momenta. So this is basically we add and we withdraw kinetic energy randomly, so we heat and cool the system. And in this fashion, the algorithm explores basically all levels of the Hamiltonian and therefore the entire landscape of the posterior distribution. And then we, at the end of the trajectory, we accept the point x prime as a new sample of our posterior distribution. We have the standard Metropolis-Hastings acceptance rule, which now just depends on the difference or the exponent of the difference between the Hamiltonian at the final point and at the initial point. And the nice thing is Hamiltonian dynamics conserves energy, therefore conserves the Hamiltonian, and we get an acceptance rate of 1 in theory, which is very nice because we have to perform a Markov chain with a very complex physics model. And in reality, due to the numerical integration of these equations of motion, we don't attain an acceptance rate of 1. We typically vary between 60 and 90% of acceptance rates, which is still very, very good. This entire algorithm is actually very nice, has very nice theoretical properties, has actually all the Hamiltonian dynamics in there. It's a tensor flow on a symplectic manifold. And in particular, it helps us beating the curse of dimensionality to a certain degree by first exploiting gradient information, because we are not blindly exploring the parameter space, but we know in which directions we should move. And second of all, we exploit conserved quantities like energy conservation, but in general you could think of extending this by adding more Noether currents, and hopefully you could then have a much, much more efficient sampling algorithm. So what we did is we basically combined the two concepts of the full physical forward modeling approach and the Hamiltonian Monte Carlo algorithm into our algorithm for Bayesian origin reconstruction from galaxies. And by now combining the physical forward modeling approach with the inference step of the HMC, we actually try to solve a very high-dimensional statistical initial conditions problem, where now we try to find the set of plausible initial conditions that can explain the galaxy distribution at the present epoch. And in particular, here in this cartoon, you see as inputs to the algorithm, we provide galaxy distributions. These are galaxy number counts, subject to noise, incompleteness, systematics, anything you want. And the BORG algorithm then exploits the Hamiltonian Monte Carlo sampling approach and the forward simulations to actually search through the space of plausible full three-dimensional initial conditions which provide explanations for the observations at the present epoch. Just to give you an intuitive overview about what the algorithm does, this is an application to the SDSS data release 7. That's one of our very early applications. What you see here, these are slices through three-dimensional volumes. In the left and middle panel, you see simultaneously data-constrained realizations of the cosmic initial conditions and the large-scale structure in the present universe. And the different realizations that you are seeing here are actually realizations from the posterior distribution. So for the time being, or here in the right panel, you see this is a corresponding slice through the data. And I would like you to focus a little bit here on this lower right corner. That's the region where we have a lot of data, high signal to noise. So you see that there are very few fluctuations. We can reconstruct the large-scale structure with high confidence, whereas in regions where we have no observations, the algorithm now fluctuates and explores physically reasonable realizations of the cosmic large-scale structure that are compatible with the observations. So basically what you see here is Bayesian statistics in its purest form. That's a numerical representation of the posterior distribution in terms of an ensemble of posterior samples. And that is basically what happens if you apply Bayesian statistics to large-scale, incomplete, and noisy observations. Yesterday there was a question on, or Orosh talked about the HMC as being numerically challenging because we would have correlation lengths on the order of a few thousands. This is from our paper from 2013, and you see that the correlation length is on the order of a few hundreds. So it's well within the regime where it's feasible. And I think tomorrow we will see that for some aspects it's even shorter. That's just a comment that it's really numerically feasible to do these things. However, when we are dealing with realistic data sets, then we are always facing a lot of problems. Apart from the actual signal that we want to recover, we have to deal with all kinds of systematics like galaxy biasing, unknown noise, and so on. And that's why we were interested actually in having the algorithm in a form that we can flexibly build data models that can be adjusted to different data sets and can account for the different systematics in a very self-consistent fashion. So we turned the BORG algorithm into something which we call a modular statistical programming engine, and basically this is just a big block sampling approach where you can now build your data models in a Lego block-like fashion by just adding different sampling blocks to this Markov chain framework. For instance, here, this is the density sampler, the HMC that we discussed before, but you might have the problem that you don't know the galaxy biasing, so you can add a parameter sampler for the galaxy biases. You might not know the noise levels, so you add a block for the noise levels. And in particular, the nice thing about this block sampling approach is that you can combine very different sampling techniques. For instance, each of these blocks could have a different sampling strategy, a Gibbs sampler, something else. Most of the time, we actually use slice sampling techniques for these blocks, which have lower dimensionality than the HMC block, because they also have unit acceptance rate and they allow us to explore quite complex distributions. So we also can sample the cosmological parameters. That's what Guillaume is going to talk about tomorrow, so I will not talk about this today. And the nice thing is that by actually having this Markov chain Monte Carlo approach, we can actually robustly marginalize out all the quantities that we are not interested in. So I want to talk a little bit about systematics, in particular those that we have to address for deeper analyses. And in particular, when we are interested in galaxy redshift surveys, we might face some foreground contamination. This, for instance, is a dust map, foreground of the galaxy. Here, this is a stellar density map, so you see that there's across the sky there are some modulations with the stellar density, and all these can lead to confusion and attenuation. So we might not be able to see all the galaxies that we want to see, but this has a signal on the sky. These are the completeness masks for low Z and CMAS sample of the BOS galaxy sample. In general, there are many, many more foreground contaminations than that what I'm showing here. You could have a look at this paper from Boris and Irania, and Boris made there a very nice compilation of a lot of foregrounds that you probably need to account for in a very detailed fashion to make very detailed predictions for or inferences of the cosmological parameters. So I just want to show you what we did is we basically take these as templates with unknown coefficients, so we don't know the strengths of the contamination, and we just add these parameters, these foreground template coefficients to our block sampling chain, and then we can infer and marginalize them out. I just want to show you what happens and why this is important for the inference of cosmological power spectra, for instance. This is an application to a mock data set that emulates the low Z plus the CMAS sample of the SDSS survey. On the left panel, you see a reconstruction of the power spectrum. That's the black stuff. The red stuff is a fiducial model. If we do not account for foreground contamination, you see that we can get really erroneous large-scale power here. We also might get some biasing here. If we account for the foreground effects and marginalize out those foreground template coefficients, then you see that we can actually recover nicely the cosmological signal from the reconstruction. So you see that accounting for all these effects will become more and more important for deeper surveys. We also have access to reconstructions of the three-dimensional density field. What we show you here is for the same analysis an ensemble mean density field. Again, here you see the reconstructed three-dimensional density field when we don't account for foreground contamination, and you clearly see these regions of where you have this excessive large-scale power. And whereas if you look at the regions where you have accounted for the foreground contamination, you clearly see that this is a more or less homogeneous distribution of dark matter. And that's great now, because you could actually also use the three-dimensional density fields to a certain degree as a diagnostics for the quality of your data if you missed something, and you might even see where something is going wrong in your survey. Three-dimensional density fields are also cool because you can also try to address a lot of other systematics. For the next generation of surveys, as we heard throughout this week, we will be facing the problems of photometric distance estimates, which are highly uncertain, and we had a lot of excellent talks throughout this week where we actually learned of how to get very precise distance estimates from the photometric properties of the galaxies. Here's something what we could add from the perspective of the cosmic large-scale structure on top of these efforts by simply noting that galaxies are not homogeneously distributed in space, but they are traces of the cosmic large-scale structure. And therefore, if we had information on the underlying density field, and you would then ask the question where to find a galaxy in the three-dimensional volume, then you might say that the galaxies are not homogeneously distributed, but it's more likely to find them in regions where the density is higher than in regions where the density is lower. Yeah? And we basically took this very naive idea. Of course, you have to extend this a little bit by accounting for galaxy biasing and everything. But the basic idea is that you combine the density sampler with a new block which now accounts for inferring the distances of galaxies from the photometric data. So you start off with a density estimate that assumes or that starts from a first initial guess of the actual distances of galaxies. You build a density field, you feed this density field into the PhotoZ sampler, and you use the density field to improve the estimates of distances from PhotoZ data. You feed that back into the density estimator, and you iterate this in this joint MCMC framework, and you're guaranteed to jointly explore the space of three-dimensional density fields and the actual distances of all galaxies from photometric data. Just to give you a very brief illustration, and this is a very naive proof of concept where we started off with just a Gaussian uncertainty in galaxy distribution. Initially, for the first sample in our Markov chain, you see this is the distribution of galaxies. You see these elongated structures here. This is the uncertainty in the distribution of galaxies. But when we iterate, you see that the picture gets sharper and sharper. And after roughly 100 steps, already we see all the clusters coming up. So you can use large-scale structure information to improve distance estimates. Again, this is a very simple conceptual idea. And just to give you some more quantitative numbers, what I did here is on the x-axis, I plot the deviation from the truth. That's delta z. In this mock test, we know the true underlying redshift. And on the y-axis, I plot the density amplitude of the underlying three-dimensional density field. So you see, before applying our algorithm to the data, the distribution of the deviation from the true redshift is independent of density. That's expected because we set it up like that. But after the application of the algorithm, you see that we get a much sharper distribution, and you see that there is a dependence of density, in particular in high density regions. We get much, much sharper constraints on the actual distances of galaxies, and that is expected because if you think, for instance, you have a cluster, a high density object that's sampled by hundreds to thousands of galaxies, so for the position of the cluster, we have a lot of spatial information that we can exploit, whereas if you go to lower densities, there are fewer and fewer galaxies actually tracing and fewer galaxies providing spatial information. So we still get a slight improvement there, but not as strong as there because there's just fewer positional information provided by the data. So in this simple test, we got an improvement in distance estimates roughly by 1 order of magnitude in the highest density regimes. This is, again, I accept any criticism for the simplicity of this model, but the idea, I think, is clear. And the nice thing is this thing would work on top of all the other estimators that we have discussed here, as long as I don't actually explicitly include information on the cosmic large-scale structure. I now want to show you one of our latest works where we actually fitted the full n-body simulation to the spectroscopic galaxy sample of this 2M++ data. That's a very shallow survey. It's extending roughly 200 to 300 megaparsecs around us. And what I show you here in this map is a spherical slice through our reconstructions of the dark matter distribution. So the dark stuff, that's the reconstruction that we obtained from the BORG algorithm. The red dots here, these are the actual observed galaxies in the universe, and you see that we get a very nice spatial correspondence between the dark matter that we recover and the actually observed galaxies. And you also see the degree of detail that we try to recover with our methods. As I said, the actual goal is to infer the initial conditions of the dark matter distribution, and here it is. So that's actually how the dark matter looked roughly the initial conditions looked roughly 13.8 billion years ago. And if you look, for instance, here in this region, then I can flip back and forth, and you can actually convince yourself that there's a correlation between these structures. So what we actually see here is the actual proto-structures of the objects that we see in the nearby universe. So apart from density estimates, what we always do is we check for the plausibility of the reconstructions. And in particular, here we made an a posteriori test of the 2-point and 1-point statistics. And in particular, if you just look here, for instance, this is a posteriori measurement of the cosmological power spectrum. And here we calculate the fractional deviation from a fiducial model. And you basically see that we get an unbiased reconstruction throughout the entire regime of modes that we are considering. And that's great. That tells us that we probably made a good job in dealing with all the systematics. And apparently, it's very consistent with what we would expect to find in a lambda CDM scenario. We, of course, get also dynamical information. This is a slice through the 3-dimensional velocity field, actually a projection along the line of sight. So the red stuff moves away from us, the blue stuff comes towards us, and in between there are regions where we see a transition of the line of sight velocity component. So these are regions where we could actually observe the Hubble flow in the nearby universe if we wanted to measure that from close by sources. There's something that I'm particularly very excited about because we now fitted the n-body simulation to the data. For the first time, we are actually able to infer the nonlinear component of the velocity fields, which you don't get if you solve for the potential flow. These are the rotational components of the velocity field. It's basically the curl or the log of the amplitude of the curl. And you can nicely see that this really traces the high density regime, so the filamentary structure in the nearby universe. Just for illustration, that's the Pisces-Perseus cluster. This is the Virgo cluster. And this is really, really new. And this might be interesting in order to tell us something in galaxy formation, for instance, how galaxies acquired angular momentum. And we are looking into those things, and it's very exciting. And also for KSZ, this might be interesting to look at. Okay, I will skip this. This is a comparison between different velocity estimates in the nearby universe. I will skip this for the moment and go back. This is again a full sky dark matter reconstruction. I want to focus on this little red blinking region. That's the coma cluster. That's our reconstruction of dark matter in the coma cluster. You see that it formed along these filaments along which mass accretes onto the cluster. You also see that it's probably not a spherical object. So all the cluster triaxiality and so on, we can have a handle on that. Most importantly, we are fitting a full dynamical model to this. Right now, and we actually can have a look or try to have a look at how the cluster formed. And that's what I want to show you right now. The next plot is going to reverse time, and we can then observe how the coma cluster starts. If you look at the upper panel right now, I identified 3 major clusters, A, B, C, and we turn back time right now. Down here you see these structures in a cartoon fashion. We are moving back in time. Now we are moving forward in time again, and you see that the structures are actually forming. So what we can observe right now, there is a merger, and right now there's a second merger, and the second merger is actually required from observations, because we know that the coma cluster is a shocked cluster. You can see this in radio observations, so that's very nice that we can get histories that are consistent with this idea. And if you look down here, for instance, you can actually see that these structures are actually orbiting, so you really see that this is the beginning of really nonlinear dynamics that we are resolving. To convince you that this is not just an arbitrary fantasy, but a plausible structure formation history, here I show you the radial mass profile around the coma cluster. The red curve, that is the ensemble mean mass profile. Light gray and dark gray shaded region are 1 and 2 sigma confidence regions, and you see that we get a nice mass profile. But down here at a few megaparsecs, we actually agree very well with complementary measurements of gold standard weak lensing and X-ray measurements. So we have a complementary way to provide some information on the masses of objects here. Just to convince you that we have not been lucky with the coma cluster, here is the Virgo cluster, here is the Shapley mass concentration, it's the same picture. And the nice thing right now is we have a reconstruction that is in spatial correspondence with the galaxy distribution. The statistics looks good, and actually if we look at the right spot in 3D volume, we actually get the actual mass that we should find there. So the summary of all these tests then probably can convince us that the reconstruction, what I just showed, is probably a plausible explanation for what we can expect to find as actual dark matter in the universe. The blue curve is homogeneous density. Yeah. I now want to quickly use my last few minutes to introduce a project by Natalia Porkeres, who is also here in the audience. And she works on extending this entire machinery from the nearby universe to the distant universe. She's actually interested in studying the Lyman alpha forest. And just to give you a very, very brief introduction, the Lyman alpha forest is generated basically when quasars, which are amongst the most powerful sources in the universe, emit their light. And this light, when traveling towards us, is passing through hydrogen clumps along the line of sight. And when it passes through these hydrogen clouds, the hydrogen absorbs some of the light, and this results in such an absorption spectrum where these peaks here, or the troughs here, they describe the absorption of light along the line of sight. And you can have this very simple relation between the flux in this spectra and the density field. We have this approximation, it's a fluctuating Gunn-Patterson approximation, where it's basically a suppression of your flux depending on the density. You have some parameters which are basically describing the astrophysics of the system, but then we have a set of these lines of sights in a 3D cube. This may look like this. And then from the set of 1D lines of sight, we want to infer the three-dimensional distribution of matter. So that's an ongoing project of Natalia, but here is a preliminary application to a mock data analysis. So you see we get a density field from it. If we zoom into this and we overlay these red lines, these are the actual lines of sights, then you can really see that there's nicely correlations, and we are able to infer information between the lines of sights. This is work in progress, so we are trying to quantify this much, much better right now, but this looks very promising. Again, we can do all the things, and something very nice right now is we get also dynamic information at redshifts beyond 2. This, for instance, you see this is a cluster region, and the vector field, this is the velocity, so you see that actually mass accretes onto this cluster. Again, here's a story in this mock test where we looked at the mass profile of such a cluster. So the blue line is the true mass profile from the mock simulation, and the yellow line, which may be hard to see, and the greenish boundary region, these are our estimate from the BORG reconstruction and the uncertainties. So you see above roughly 2 megaparsecs, we get back the dark matter from the baryonic model. Admittedly, this is a mock test. In reality, we'll be facing many, many more problems, but this is a very encouraging result so far. One of the challenging things here right now is we have to simultaneously solve for the three-dimensional density field plus additional parameters that account for the noise in the system, but also for the astrophysics. And so we have to solve this via our meta-sampling approach. And I just want to point out that we can actually end up with very nasty distributions like something like this here. And that's probably why we want to have a sophisticated Markov chain approach. I think a simple optimization scheme might get stuck somewhere. This is really, really hard to do this, and we are struggling quite a lot with this, admittedly. I think I will skip this one and just summarize. What I wanted to show you today is that we can basically now develop data analysis methods where we actually incorporate the entire theoretical framework of a cosmological large-scale structure immediately into the analysis framework. That's the BORG algorithm, which basically fits n-body simulation to the data directly. So we can account for the dynamics in the system, and we can really account for the nonlinear and non-Gaussian statistics in the large-scale structure that we have to account for. We have a framework where we can build very flexibly very different data models that we can put into the framework. We are a combination of the Hamiltonian Monte Carlo sampler and a block sampling scheme. We can deal with a lot of systematics like foreground contaminations, meta-parameters of biasing models, noise, and so on. And of course, we can try to do this in a very high-dimensional scenario. Science-wise, we get a new interesting window to studying the initial conditions, not only statistically, but we also see the protostructures. That is interesting, for instance, maybe studying galaxy formation, tidal torque theory as a keyword also. And we see that we get very accurate and detailed reconstructions of the dark matter field. And for the first time, we are actually also combining these reconstructions over many different scales and across many different probes of the dark matter. So we have used galaxy clustering, number counts, and we are agreeing with weak lensing, X-ray measurements to a very high degree of accuracy. There is something new and exciting that we can do. We can have a look into the dynamics. I'm particularly excited about the nonlinear aspects of the velocity field, which is really new. And in general, what we arrive at is we get a pretty consistent and dynamical picture of the universe and the mass surrounding us. And I think that's really nice, because with these kinds of machines, we can actually start becoming physicists again, rather than being a data scientist, because now we can just plug in the physics model again. We can start modeling the physics in the data analysis framework. So thank you very much. And if you want to learn more about the Aquila Consortium, you can visit us at this webpage.
Any questions? Sure.
Is the vorticity mass weighted or is it volume weighted?
This one is volume weighted. Yeah.
How do you compute volume weighted? Because you have the particles, right?
Yeah, we estimate the density fields and then the velocity field. So this gives us a momentum field, and then we scale out the density.
But then it's still the momentum, right? So you average of a momentum and divided by the mean density. Okay, okay.
Sorry?
You divide by the mean density or the actual density?
The actual density at that position, yeah.
But that's still averaged over the cell, no? That's still averaged over the cell.
Yes.
Yeah.
Yeah.
Other questions? Yeah, behind first.
For those cluster mass profiles, how did you do the error bars for those? Was that based on the posterior, best fit signal, and you just evolved all those forward to get different mass profiles?
Exactly. So you have an estimator for this mass profile, right? And you can apply it to all the samples of the Markov chain, and that's where you get your error bars from.
Let's see, two quick questions. Have you looked at the whole ensemble of forming the coma cluster? How different do the different histories look?
No, not.
So this was just showing like the mean posterior or the...
This was, admittedly, this was one realization that I showed.
It was just one random.
This was just one.
Yeah,
but,
okay.
That's something which we're investigating right now. So we are looking at the histories and also trying to look at merger histories. And so I don't know if Guillaume is going to show something about this tomorrow, but this is a work in progress, actually.
Are you starting to extract statistics of merger trees and all that stuff? Okay. And then another, are you planning on releasing, like I can imagine people using small sections of this to be initial conditions for much higher resolution, smaller clusters. Is that part of the thing you guys are, okay.
Yes.
It's an obvious idea.
Yes. So one obvious thing of that is to do constraint simulations. And there are several projects that we are trying to do. One of the projects that we are doing with people from Helsinki and also within the Virgo consortium, Simon White and Carlos Frank, is to actually provide initial conditions for the local universe to see if galaxies, if Milky Ways form and so on. And one thing why this is interesting for that is because the tidal fields seem to be important. So have large-scale reconstruction. So all this is work in progress where we look into this. Something that we are particularly interested in is also not only the local universe, but for instance have a very detailed constraint simulation of coma cluster and other features that we see. And then also cross-correlate with observations like, for instance, we could KSZ or SZ, see X-ray, and just see what happens. Yeah. Absolutely, yeah.
Okay. How do you estimate degeneracies between models, especially when you consider at the very beginning, you consider that potential for the initial condition? How do you estimate that, for instance, this potential, another potential, or another set of parameters in the model cannot make more or less the same, give you the same final result which fits well the data?
So I'm not sure if I understand your question entirely, so I will answer and you tell me if I answered your question. Okay. So what we are doing is actually we are exploring the entire posterior distribution. So the ensemble of potentials or density fields that are actually able to explain the observations that we make in the present universe. And of course, there may be density fields which are very similar and can give the same results, but we are never making the claim that we have a unique recovery. That is not possible. We can only make an ensemble of predictions. For instance, when you look at a cluster, right? In the present universe, this is a visualized object. Yeah. So, and if you move the cluster back, it becomes large because the protostructure is large. But let's say within the contour of the visualized halo, when you propagate it back, you might not be able to distinguish between different initial conditions because the information got lost through the variational model. So, and that is what the Markov chain actually does. So the Markov chain will explore all possible realizations of fluctuations inside the this region which would be collapsed and will result in the same predictions for the data. So if you have something in the data that can break this degeneracy, this will give you a more constrained reconstruction for those things, but if not, you will just homogeneously fluctuate about different realizations that you have. And that's the entire idea about the Markov chain Monte Carlo approach, that we are not able to provide a unique answer, but we want to have the ensemble of plausible answers in order to quantify exactly these kinds of uncertainties.
And can you give a sort of a probability to this ensemble of when you explore the Markov chain between different models? Can you give a probability?
Yeah, I can show you. I think I have a slice. Yes, I can show you something like this. This is a very crude example of this. So this is a work by Florent Leclerc, who is interested in actually classifying structures, and this is a simple example where he tried to classify clusters and voids. And And what you can see here, basically, you see this is basically a detection probability. So basically he ran over all these ensembles and he ran this classification algorithm, and then he just counted in how many of these ensembles we got a cluster at this position in the initial conditions, and these are the voids, right? And the nice thing is, you see initially this is almost equally distributed. That's expected for a Gaussian random field, and you can play the same game for the present universe, and you see that those voids on average expand and the clusters collapsed, and again you have the detection probability that we can give. So that is something we can quantify, and Florent has invested a lot of work in doing this in a much, much more sophisticated way, but yes, we can assign probabilities to that.
Yeah, the last quick question to Lucia.
So I understand that you marginalize over the cosmology too, right?
Not in this case.
Ah.
In this case, we fix the cosmological parameters. That is something what probably Guillaume is going to present tomorrow. Okay. We have actually added now a cosmological parameter sampler to this, and that's work in progress, and it looks very promising. So we are starting to marginalize out the cosmological parameters as well. Or if you want to have some cosmological parameters, we are margining out the density field, whatever you prefer.
Right. Oh, okay. So then that explains why the results are in megaparsecs.
Sorry?
That explains why the results are in megaparsecs. Because if you don't know the cosmology, then as you vary the cosmology, your map between redshift to megaparsec will be different, and therefore you would have an uncertainty also on how you present the results.
And that's a part of the project that will be demonstrated tomorrow. Thanks. So yes, we are working on these things.
Okay, so maybe we can close the session for this morning and have a lunch break now.